And I'm presenting this project on behalf of Jorge Pineda, who is the PI of the project. And this is a balloon project to carry a heterodyne receiver at stratospheric altitudes. The main aim of this project is to study the regulation of star formation in galaxies, since we all know that the formation of stars is very inefficient, converting only a few % of the interstellar medium mass into stars. And we want to understand how this is slowed down. The main slowing down physics is probably stellar feedback. And this has, of course, important issues on the galactic evolution itself. And so to understand this feedback, we want to observe and model all the different phases of the interstellar medium, and but also look into external galaxies, because being inside the galactic plane, you know, we have only a limited view of what goes on in our own galaxy. It's detailed, but it's limited. So the life cycle of interstellar medium, I'm just recalling it, but I think everybody knows that, as 5 phases. One, and I won't discuss, which is a hot medium at above 1 million degrees, but we have warm neutral medium and warm ionized medium, both at 8,000 Kelvin, with cold neutral medium from atomic hydrogen at 100 or 200 Kelvin, and then molecular clouds, which can be cold or hot, depending on what goes on inside them, with the H2 regions at the inside or at the edges of these clouds. To study them, far infrared lines are very useful. There has been a lot of work done with C+ already, and there is also some work being done with oxygen, thanks to Sophia in PDRs. But also Fifi is useful for very ionized species in the very hot medium. The C+ is everywhere, as you can see on this slide, because its ionization potential is lower than hydrogen, so it's easy to ionize. And also it's easy to excite with electrons, atomic hydrogen or mercury hydrogen. So it's quite tool for everything. However, a lot of studies have been done in the galaxy with Herschel and with Sophia for this C+ line, but they mostly give information about neutral gas and not much about the ionized gas component, which is the first one which is produced close to the massive stars with their feedback. And so we want to study now the ionized gas regions. And for that, well, I'm going a bit too fast, sorry, because this is not my slides. I'm not completely familiar. And I had to say that these H2 regions produced around the stars start being very dense, and they expand. So the ultra-compact H2 regions are very dense, and while they expand, both because of the UV eating the molecular cloud around, and the stellar wind also pushing the gas all around, injecting momentum in the cloud. You get the H2 region which expands, and with its density decreasing, and eventually there are holes in the cloud which make the ionized gas expand as champagne flows in the diffuse medium. And so these ionized regions are very highly inhomogeneous, and we all know the famous pictures of pillars, like the pillars of creation, clams, horse head, and so on. And this is varying a lot, so we have to measure all these densities, and also we have to measure the velocities of this ionized gas to try to make a 3D picture of the ionized medium. For that, we have one very nice tool, which is ionized nitrogen, which is an excellent tracer of ionized regions, because its ionization potential is above the one of hydrogen, 14.5 instead of 13 point something. And so it can be only found in places where hydrogen is completely ionized, which are H2 regions or the warm ionized region. And the second advantage of nitrogen, ionized nitrogen, is that it has two fine structure lines at 120 and 205 microns, so both in the terahertz regime. And the ratio of the two is a direct measurement of the density of electrons. As you can see on this plot, the ratio of the 122 to 205 here depends directly on the electronic density. So this is a nice way to measure the electronic density in the ionized region. And if you use heterodyne receivers to get the velocity information, you might get in the end the 3D structure of these regions you are looking for. So this kind of work has been done already. And Paul Goldsmith published a paper 6 years ago from PAX measurements of a number of sight lines of both nitrogen fine transitions. And the surprise came that they found electronic densities between 10 and 50 per centimeter cube, while the warm ionized medium would be much lower than that, about 0.1, and H2 region should be above that. So they are wondering whether that's an average on the line of sight, or that's clamps, or what. And because PAX has no velocity resolution, they could not tell, and that's a good reason to move on to heterodyne receivers. So, of course, SOFIA has this kind of heterodyne receivers, but SOFIA is not flying high enough, on top of the fact that it's polluting a lot. And the SOFIA, normal SOFIA transparency at 2.5 terahertz is limited by this huge water line here, which is H2O 432 to 423, and making it optically thick. And even if it goes up to 14 kilometers, it's still not very good. With a balloon, already at 30 kilometers, 31 kilometers, you get full transparency for the ionized 122 micron line, and relatively good transparency for HF, which I will 2 to 1, which I will discuss later on. And if you go up to 40 kilometers, here, this was computed for 40 kilometers for our seed balloon project. It's even better. You see the water line is getting very quickly, very narrow, and making observations of these lines much easier. Even the water line itself might be observable with enough Doppler shift, but I have not put figures into that. So to do that, we need a heterodyne receiver, fine. Higher than SOFIA, fine. No satellite in the future, so we have to go to a balloon. And this is the ASTHROS project. We will have a 2.5 meter telescope with a zero pressure balloon. So its altitude of flight is not exactly controllable, but between 30 and 40 kilometers usually. It will start from McMurdo Antarctica base, and it can fly typically 3 weeks and can go up to 2 months. It will carry 2 cameras of 4 pixels each, one for the 122 micron and 112 micron HD, and another one for the 205 micron. With there will be no liquid helium on board. It will be cryo-coolers with low consumption ones, so they can fly very long time. With a liquid helium, it will be only a couple of days maximum. And solar panels, of course, because again, batteries which are usually used on balloon projects would not last several weeks. And while that's a typical balloon project with a pointing between -5 degrees and 65 degrees, above 65 degrees, you're blocked by the balloon itself. And so you can do Earth limb observations also for the same price to observe OH lines, for example, which is very keen to atmospheric physicists. And it can be reused and improved relatively easily, and it's relatively cheap. And there is no CO2 to make it fly, which is very good news. So for 3 weeks, we have, of course, 3 days commissioning. And then we spend 1 week to map a couple of H2 regions in our galaxy. Another week to map a full galaxy. And then a couple of days to do protoplanetary disks like a TW Hydra. And then we are open to an extended mission period, which we can call an open time period. It will be open to ideas by the community. Of course, it's not during the flight. We are going to ask for people to decide what to do. It will be beforehand, but we can plan things to be done without promise to them to be observed. But if the time is there, they will be observed. I will mention that a little more later on. So the first goal, which is this N plus observations of 2 H2 regions, are G336 and Carina Nebula. The main difference between the two is the Carina Nebula has already suffered some supernova events and not the other one. So this is interesting to compare the feedback mechanisms in presence of supernova remnants or supernova mechanical action or not. And both will be about a square degree mapping with a high sensitivity, and resolution is a few kilometers per second because that's enough for these kind of lines. The second part will be to map this M83 barred galaxy, to have the large-scale features of electronic density all around the galaxy, to see how this electronic density compare with the bar, with spiral arms pattern, and so on. And finally, we will spend a couple of days integrating for the HD line at 2.7 terahertz, 112 micron, with a high spectral resolution. Here we will go down to 30 meters per second. So we need a long integration time because the source will be diluted and the spectral resolution will be high. But what we will get at the end is a velocity resolved line to which we can compare to the rotation curve of the disk, which will be provided by ALMA observations, or which is probably already provided by former ALMA observations, to tell where is the mass spread over the disk. So I heard in several of the previous talks that HD is considered to be the best tracer to measure mass protoplanetary disks. But in the former PCMI conference we had a couple of weeks ago, this was highly contested by some people, saying that in class 0 and class 1 objects, that was not at all true, because there are, I think if I understood correctly, that's too cold for HD to be excited, since the upper, the T=1 level is 140 Kelvin above ground. So you need some heat to make it glow. Then Trapman mentioned that it was relatively precise within a factor of 2 for low mass PPDs like TW Hydra. But if you add the 2-to-1 line, which is of course not in a balloon, you can improve a lot the precision of the determination of masses from HD observations. So that could be a start. Finally, beyond the 3 weeks of observations, we can do other lines. So the HF10 has been detected with the KO and then with Herschel, and we know it traces H2 in the dark regions. Yeah, thank you. And the 2-to-1 line will be available here, and I know some people mentioned it would be interesting to measure it in circumstellar envelopes. and OH, some H2 lines, providing we fly at 40 kilometers and the Doppler is sufficient. We have to put numbers there. Some CO excited lines, and maybe also HUD plus ground transition, but I'm not sure the receiver goes down that far. So this is to be checked. And also we want to do some TeraHertz survey in a couple of sources to be determined. And we are open to community propositions, of course. So I won't go through this, which was Jorge vision of the future. And I want to insist on the fact that now that the balloon can fly 3 weeks, which means 500 hours, and if it's 2 months, it's 1,500 hours. It's completely comparable to Herschel, which spent only typically 1,700 hours per hi-fi channel over its 4 years life. So it's completely comparable at a much lower price. So balloons are a very good alternative to for small telescopes, of course. We're not going to send a 10-meter telescope on a balloon, but for small telescopes, it's a very good alternative to spacecraft, and much cheaper and very little CO2. So thank you for your attention.
Okay, thank you. First, Jérôme, a question? No?
Jérôme always asks questions.
Okay, so we start with Christophe.
Yes.
Yeah, the first one was just a comment to say that for Sophia, that's the goal. That's why they go to the southern deployments to New Zealand. There, then the water vapor they can get, it's below the micron. So you can get 1 micron or lower. So that makes it then interesting. You can also do that perhaps with Sophia in the southern deployments.
Why is it better in the southern hemisphere? You know why?
Maybe Robert can comment on that. I'm not sure, but I think it's much colder, probably drier and colder.
Yeah, yeah, it's colder. You're farther south than Palmdale, for example, or Germany or whatever.
It depends. They just went to Tahiti this year and it was awful.
I can imagine.
They can't go to New Zealand, so they're considering Santiago or Buenos Aires now.
Yeah, Tahiti is almost at the equator, so
it's awful. Yeah, it wasn't very.
But that was because of COVID, right?
Yeah, because we can't go to New Zealand.
When Peter Schilke tried HD observations, it was from New Zealand, and he said that the weather was very bad and couldn't get much transparency at 2.7 terahertz. But maybe it's a question of luck.
It can be too.
Sue, you had a question? Suzanne?
Yeah. I just wondered, and specifically, how does the ASTHROS telescope, which is already approved to fly next year, how does it I mean, Gusto, how does Gusto compare to ASTHROS? Gusto is a smaller telescope, but it will launch next year is for sure. And it's one of these ultra long duration balloons, right? Many months it goes, and it will do these lines, a lot of these lines.
No, they're not going to do N+ lines.
Yeah, they are. 205 micron. So
yeah, but the 205, but you need both of them. But 205, you can also do it with Sophia. I mean,
you can do 122 with Sophia. We've done that a lot. So I mean, yeah, depends.
Yeah, the main point is the 122 micron line for which you get this heterodyne data, and it's only. But I don't think NASA would have approved both Gusto and ASTHROS if they were doing exactly the same thing. You know?
But ASTHROS isn't approved yet, right? It's in the
no, it is approved. It's being built, and we are ready. We're not behind the schedule despite the COVID crisis. So they're on time on the original schedule, and we are really going to fly in December 23. If nothing bad happens in between. No, it's going to fly in 2 years' time.
I wonder why. Okay.
Okay. Well, thank you, Laurent, again.